In this video, I want to talk about the particular solution. Okay, what is the particular solution to a differential equation? So a particular solution is one that satisfies the boundary condition that is indicated in the problem. So let's say for our three examples that we are going to solve in this video, the boundary condition is stated here, no? So first, when x is 2, y is equal to 1. So in the second problem, that is when t is 0, r is equal to r sub e. Okay, and then for the third problem, when x is 0, y is 0. So those are particular boundary condition. So you will insert this condition once you know the general solution. So that's the first step. Know the general solution. The first step is to solve for the general solution. Okay. Let me erase that. Know the general solution of the problem, and then after that, substitute the boundary condition. Substitute the boundary condition. We'll actually solve for c, the particular value of c, and then return c to our general solution, and then you will now, after returning and some simplification, you will now obtain your particular solution. Okay, so that's the general steps that we are going to take. So in the first problem, I will just select our first problem. So let's go ahead and just write it here. Our first problem, we have x, y prime minus y squared is equal to 1. And the condition later on is that when x is equal to 2, y is equal to 1. Okay, so let's go ahead. This is a derivative of y with respect to x. So if we put it in a differential form, xy differential y minus y squared differential y is equal to differential x. And then next is I will group the terms with differential x. Xy dy minus y squared dx minus dx is equal to 0. Xy dy minus quantity y squared plus 1 dx is equal to 0. So next step, this is what we did with the particular solution or with the general solution in the previous video. So I will now multiply a factor which would separate the variables. So here, what we are going to multiply is 1 over x times y squared plus 1. Okay, so multiplying that, the first term will be simplified to y dy over y squared plus 1. And then, the second term will be dx over x is equal to 0. So what we can see here is we can solve these two, we can integrate them using the formula or the integration formula du over u. So for the first part, your u is, or for the first term, the u is y squared plus 1, and the differential of that is 2y dy. So if I will integrate, I will have a balancing factor of 1/2, and then the other one is simply dx over x. So let's go ahead and put our answers here. I will now have 1/2 ln of y squared plus 1 minus ln x is equal to c. Okay? So we can still simplify this by combining the logarithms in the form square root of y squared plus 1 over x is equal to c. And as a further simplify, if we will solve for square root of y squared plus 1 over x, so it will be equal to e raised to c, and e raised to c is still equal to c. So it's now time, since we now have our general solution, it's now time to solve the particular solution. So as I've said in the step, we substitute the boundary condition. So the boundary condition that we have in the problem is that when x is equal to 2, y is equal to 1. So let's substitute that to our general solution. So we have the square root of y squared plus 1 over x is equal to c. Okay? So we have 1 squared plus 1, the square root of that, divided by 2 is equal to c. So now we see that c is equal to the square root of 2 over 2. Okay? So the next step is we will substitute c back to our general solution to get the particular solution. So we have square root of y squared plus 1 over x is equal to square root of 2 over 2. We can simplify this equation by squaring both sides. By the way, the given is, in our given, we have y prime. This is derivative of y with respect to x. Okay, indicating that y is our independent or our dependent variable. And this is our independent. So therefore, this comes from derivative of y with respect to x. As we all know, it comes from a function y is equal to a function of x. No? It means that it comes from that, y is equal to a function of x. So what we want to do here, we want to solve for y. Okay, in our particular solution, we also want to solve for y. So we go back here, we square both sides. We now have y squared plus 1 over x squared is equal to 2 over 4 or 1/2. Let's cross multiply. Or we now have y squared, because we want to solve for y squared. So let's just cross multiply x squared. X squared over 2 is equal to x squared over 2. And finally, y is equal to the square root of x squared over 2 minus 1. So if you still want to simplify that, we can have the square root of x squared, then 2 will be our LCD, and then minus 2. So that is our particular solution. Let's go to our next problem. So in our next problem, we have again the derivative of r with respect to t, indicating that in our final solution, we need to solve for r. Okay, so let's go ahead and put this in a differential form. Differential r is equal to negative 2r t differential t, differential r plus 2r t differential t is equal to 0. So what we need to multiply here is simply 1 over r. So after multiplying 1 over r, I will now have differential r over r plus 2t differential t is equal to 0. So you can see here, it's now elementary. We can simply integrate, and it will produce ln r plus t squared is equal to c. So we automatically have our general solution. So next step is to substitute this condition that when t is 0, r is equal to r sub e. So ln r sub e plus 0 squared is equal to c, or c is equal to ln of r sub e. So let's substitute that. Let's go ahead and substitute this to our general solution. So we have ln r plus t squared is equal to ln of r sub e. So remember that we, in our particular solution, we want to solve for r because that r is our dependent variable. So we want to make this as a function of t. Okay? So let's combine ln r minus ln r sub e is equal to negative t squared, and we can combine using properties of logarithm. Ln r over r sub e, and then finally we have r over r sub e is equal to e raised to negative t squared. Solving for r, as I've said, r is now equal to r sub e times e raised to negative t squared. So that is our particular solution for problem number 2.